All right, hello, Grayson physicists. This video is to kind of just give you a little bit extra help with the practice problems for our lesson on today, which is Wednesday, August 12th, our first day. And that's partly because in the live session this morning with third period, we didn't quite get the time to go through all the practice problems. And I also want to show you what working through some questions on EClass is going to look like. I know some of you have plenty of experience that with other classes or other teachers previously, but maybe you never really have done work through an assignment on EClass before. And if that's the case, this should help you out quite a bit. So I've got our physics EClass homepage pulled up here. And I also want to show you just, there's a couple of different ways you can get to a particular assignment. And by the way, you'll notice it's sort of a gray block sort of here, and that's like kind of overlaid over the screen. And that's where I'll be making some notes when we work through some of the examples. So anyhow, if you go to just the announcement post here today, you'll notice it says here, it says when you are ready to participate in class on Wednesday, August 12th, click here. And so I'm going to do that. And this took you to your daily instructions for today. And most of you should have seen this at some point, although it's certainly possible that if you just joined Zoom directly earlier in third period with the emailed link I sent out, you may not have looked at this yet. So definitely make sure you look into this or log in to look into this. But anyway, it breaks down the instructions in terms of both synchronous students, which is only third period today, and asynchronous students, which is only sixth period today. At least those are my only two physics classes. My other classes are astronomy. So again, here's just kind of going back over what you would have typically started the day like. This would have been your link for the live session if you were synchronous today. And then later I went back and added this. This link right here is the recording from today's live session. That was not there earlier, of course, that's been added since. And then it says for synchronous students, the third step is to make sure to answer the EClass questions. That's what we're going to be looking at here in a little bit. After we go over the practice problems, we'll look at the actual assignment questions. We'll look at two of them. And then lastly, it says participate in this discussion topic. Now, by the way, one thing just to make sure you're aware of, both the assignment questions, the AKS 1A classwork, and the discussion topic are something I'm looking for you to have completed by this Friday, which is the 14th of August. So again, I know lots of issues today with being able to log into EClass. But the assignment itself is pretty short, and between the shortness of the assignment and the availability of it until Friday, I think you should be able to get it in by then. So that's what I'm looking for anyway. Let me know, email me if you have questions about that or some sort of issue with getting it turned in by that point. And for asynchronous students, your instructions are almost the same. The key difference, of course, is that you have the pre-recorded version of the lesson here. Now, one thing that's kind of an advantage with if you're a sixth period student and it's an asynchronous day, you kind of have your pick. You can either watch the pre-recorded lesson because it'll be here regardless. A lot of times that'll be something that's coming from a different physics teacher at the high school who's recorded it for the whole physics department. But if you're a sixth period asynchronous student on a particular day, and third period was synchronous that morning, they've already participated in a live session. You can just watch my live recording if you want to. You could watch either of them, both of them if you really want, whatever. But the live recording will always be me, unless like I'm not able to actually, for whatever reason, do like if I actually have to be out one day, maybe I have doctor's appointments or something like that. There would just be a pre-recorded session. But anyhow, for the rest of the asynchronous stuff, you have the link to the Google Slides, so you can work through that on your own. That's something we did together in the live session this morning in third period. And then the link to the classwork and the link to the discussion topic. Now, so what I want to do is I want to go ahead and go to the Google Slides document. I've downloaded that separately or offline as a PowerPoint. So I'm going to just pull it up here. And again, what I'm going to focus on is the practice problem, or the practice problem in the equation sections. And here are the equations. And it says write these down. And you will need these today and in the future. One reason why it says write these down is because when it comes time for us to take our test, which our first test is not far in the future. In fact, let me double check my calendar here. Yes, our first test, I believe, is scheduled for the 27th. So if that were to change, I will let you know. But yeah, Thursday the 27th, that's what we're looking at for now. So anyway, my point is that on a test, you want to have the equations in front of you to look at. But when you're working on the test questions in eClass, they're not going to be provided in the questions themselves. So I would write them down now, or sometime when you're viewing this slide from the PowerPoint/Google Slides, we'll copy them down on some paper that you can keep in a binder or something like that, and have ready to pull out during a test. If you can memorize them, that's great, but that can, you don't want to accidentally misremember it during a test or something like that. So I wouldn't really do that. You can also, of course, print these out. If you're using a printer, that's fine too. But we know not everybody's using one or accesses one or whatever. All right, so the 4 formulas here. We have really 3 different things we're dealing with here. And actually, you could really kind of say that there's 5 formulas on the screen, because you can kind of see how acceleration is shown in 2 different portions. Pardon, excuse me. But the simplest one, and the one we'll start with here, is speed. And that is simply dividing the distance that an object has traveled by the time it took to travel that distance. So, well, we have an example practice problem. We'll get to that. But anyway, distance over time. That's a really simple formula, and it's a division problem. One thing I will point out is that if you're using a calculator, you're typing this in on a calculator, the distance, because it's the numerator, should always come first before the time, which is the denominator. I've seen that come up as a point of confusion before with some of my students. All right, for velocity, you'll notice both of these say velocity average, or just average velocity. That's how we'd say it normally. There are basically 2 different methods they're giving you here to calculate average velocity. The top one is the one you'll use most often. And it looks kind of weird. It says triangle x over triangle t. If you know from chemistry or perhaps some other courses, the triangle here is actually the Greek letter delta. It's their version of the letter D. It's the uppercase version. And in a formula, delta in this context means change in. So what this really says is change in x over change in t. Okay, good. But what are x and t? X here stands for position, which is basically just your location. You can even, if you want to try and really simplify it, you can even think about it as a point on, like, say, an x-axis. That might help you kind of remember, with the variable x here. So, like, if I have something move from left to right along a flat x-axis or something like that, it's changed its position, going 5 meters, 5 feet, whatever. And then delta t is change in time. Now, the whole delta or change in part of this equation is a little unnecessary, just because typically on most of the problems we're going to work with where you would calculate average velocity, the amount of distance that has been traveled or the amount of displacement that has occurred is going to be equal to delta x, the change in position, and the amount of the total amount of time given is usually going to be equal to the total amount of, the change in time. In other words, if they give you a question that says, hey, calculate the velocity, and they tell you there's some amount of distance or displacement involved, or they tell you, and in addition, they tell you a certain amount of time has passed, those 2 things are usually all you need to fill in here. You don't usually need to actually calculate a change in position, meaning subtracting one from another, or a change in time where you actually subtract, again, one from another. So in other words, this formula for average velocity is really just kind of a different way of writing what we did for speed. A change in position can be interpreted as some traveled distance or some amount of displacement. And that, again, that's going to be measured in feet or meters or something. And then a change in time is just how much time has occurred during that movement. So if you divide how far something has gone by the amount of time it took to move, then you're really doing the same thing to calculate velocity as you do for speed, most of the time. There can be some exceptions that come up, and we can address those later. Another way to find average velocity, if you don't know the displacement or distance that the object has traveled, and you don't know how long it took to do that, but if you do know 2 different velocities that it's had, like it went a certain velocity earlier and then a different velocity later, we call those the initial and the final velocities, VI and VF. you can literally just find the average of those two numbers. You can add the initial velocity, which is the earlier one, to the final velocity, which is the later one, and divide by 2. So that's another way to find average velocity if the information you're given is two different velocities instead of an amount of displacement or position or distance, and of course time. Now, for acceleration, acceleration's a little different. This one here, the deltas do start to mean a little bit more in terms of something you really have to deal with. But again, it's really only for one of the two. So if you look at the formula for acceleration, it says acceleration is equal to delta V over delta T. Well, delta V is, again, delta is still change in. So V, of course, here being still velocity. So we have change in velocity. And that phrase, change of velocity, a changing velocity, anything like that, should at some point pretty soon, the next few days, definitely by sometime next week, so it should automatically alert in your mind to think, okay, we are dealing with acceleration. In fact, we could really say that the definition of acceleration is a change in velocity. So the formula here very nicely just points that out for us. It says acceleration is equal to a change in velocity over a change in time. And that's because mathematically speaking, acceleration is a rate of change of velocity. How quickly does that change occur? That's what we mean by rate in this case. So delta V is change in velocity. And then this is here where you really do have to actually find the change, the difference. And so we mentioned a moment ago, we mentioned an earlier initial velocity for an object that's moving and a later final velocity for that same object. If we want to find the change in velocity, then we need to find the difference between how fast it was going earlier and how fast it's going later. And to do that, we're going to have to subtract the earlier amount, the initial amount, VI, from the later amount, VF. And so it sounds kind of strange, perhaps, at least, again, in the past, I've had students who got a little mixed up about this. But in the acceleration formula, if you're going to write it out like you see here, VF will come first in the formula instead of VI. And that's just because of how subtraction works. So anyway, VF, final velocity, minus initial velocity divided by time. And we'll come back to an example of that in a moment. So let's look at our, again, here's just a quick reminder in the slides of what you're supposed to do here. We're going to look at the first two practice problems, or the only two practice problems, and then we'll look at a couple of the actual assignment questions. All right, so a girl travels, practice problem number 1, sorry. A girl travels 20 miles on her bicycle, and the trip takes 2 hours. Express, sorry, I'm moving my little block here. Express her speed in miles per hour. And it says, first we identify the variables of our problem. Distance, or D, equals 20 miles. Time, or T, equals 2 hours. Now, if we go back to our formula sheet, again, this question, sorry, one more time, it said express her speed. So we need the speed formula, distance over time. So I'm going to turn on my drawing function. Speed, which we can just write as S, equals distance over time. And again, we've identified our variables. We said that the distance was 20 miles. And by the way, just so you know, drawing with a computer mouse pad is not my forte, but I'm going to try and make it work here. And so we're dividing that distance of 20 miles by our time of 2 hours. Okay, and so again, the nice thing about this speed formula, and really, like I said, the velocity formula too kind of works out the same way most of the time. It's a really simple formula. You're doing one division problem. It's a one-step formula. You're dividing by the distance by the time. So 20 divided by 2, well, that's 10. No problem. Double check on the calculator if you want. Also, with the units, we are dividing miles by hours, so that's what we're going to write. Speed doesn't have its own little unique unit. Like we're going to see later on that force, for example, is measured in newtons. So it's got its own little unique unit. Speed does not. Neither does velocity, neither does acceleration. Instead, their unit is made up of kind of like what you used in terms of time and distance to make up or to mathematically get to your answer. So if you like, for example, if you look where it says miles per hour here, miles per hour, it's really a division problem by itself. It's like a fraction, miles over hours. And that's what we did. We did 20 miles over 2 hours. And so we got 10 miles divided by hours, or 10 and then miles per hour, excuse me. All right, so that's all for that one. That one's pretty simple. Like I said, speed problems like this are always pretty easy. So practice problem 2, though, is a little more difficult. Not too much. All right, let me redraw my little field here. A little drawing field. I'm gonna make this one a little bit bigger. Change my marker. Okay, so now we have practice problem 2, and it says a car starts from a stoplight, I'm emphasizing that for a reason, and is traveling with a velocity of 10 meters per second east in 20 seconds. What is the acceleration of the car? So again, it tells us what it wants us to find. It says find the acceleration. So I'm going to go back to my formula sheet and find again the acceleration formula. Now, one thing you might be confused about if you just look at this, if I'm going to write out the acceleration formula, I write out either of these. I either write A equals delta V over delta T, if I'm comfortable with that version, or I write A equals VF minus VI over T, if I'm comfortable with that version. You don't write out this whole thing. The formatting makes it look like you should. You don't need to. Delta V is the same thing as VF minus VI. Delta T is the same thing as the total amount of time. So with that in mind, I'm going to go ahead and draw out write out our formula. A equals VF. I'm going to do that version. I like the second version better. VF minus VI. Oops, lost my drawing thing. Here we go. Got it back, I thought. There we go. That's supposed to be a V. All right, VF minus VI over time. All right, so again, now we got to identify our variables. So it says VF is 10 meters per second and VI is 0 meters per second. Now you might be wondering, well, why? Why is VF 10? Why is VF 0? Where did you get 0 from, Mr. Williams? Where is all this coming from in the question? So this question is very similar to a lot of car ads that talk about the acceleration rate of the car, so especially sports cars. Maybe you've ever seen a commercial or read seen an ad that says 0 to 60 in 5 seconds or something, or that would actually be kind of long, right? That amount of time, 0 to 60 in 0.8 seconds or something. I don't know. So maybe that's too quick. But the point is a commercial like that actually lays out an entire acceleration problem for you. And this question is pretty much the same kind of thing. It says the car starts from a stoplight. Now notice again, it said stoplight, meaning it's starting from a stopped position. In physics, a lot of times we'll say at rest. If something is at rest, it's not moving, the velocity is 0. So it's starting at a velocity of 0, it's not moving. So that's our initial velocity. VI is 0. And then it gets up to a speed of, or a velocity of, 10 meters per second. So that comes later. So that has to be the final velocity. And again, it takes 20 seconds to do this. So that's going to be T. So filling the formula in here, A equals, let's see, we said 10 meters per second for final. And like I said earlier, don't forget that with this formula, when you're writing it, the final velocity comes first. You're subtracting the initial amount of velocity from it, not the other way around. So 10 meters per second minus 0 meters per second. When I draw a 0 by itself, I like to put the little slash through it, which is kind of a habit I've picked up, just so you don't think it's an O. And again, we're going to divide all that by the time amount that has passed, and that's 20 seconds. Okay, so there's our formula with everything plugged in. and we're going to do 10 minus 0. Ooh, that's pretty easy. And that's one thing, whenever you have an acceleration problem where your initial velocity is 0, that makes the whole thing really easy. It kind of turns what's supposed to be a 2-step problem into a 1-step problem, because you all know what 10 minus 0 is. You don't really have to think about it. It's just 10. So what we're going to get then is acceleration equals 10 meters per second over 20. And I know some of you can kind of figure out where the rest of this is going in your head pretty quickly, but just for the sake of everybody, I'm going to include this step here. So that's 10 meters per second. That's supposed to be an S, not a 5. It's kind of better. Divided by 20 seconds. And now it becomes really easy because you can see it. Because we have an initial velocity of 0. This is really, again, a 1-step formula. 10 over 20. Well, that's 1/2 or 0.5, like it says here on the PowerPoint slide. So this is going to equal, and I'm just going to write it in fraction form. So this is equal to 1/2 meters per second per second. Now we're going to take a second here and talk. We're going to take a moment here and talk about this unit. Again, we just divided meters per seconds, excuse me, by seconds. And I've written that back out here. I've written meters per second over seconds. If we want to kind of contract that visually, we can rewrite that as meters per second squared, like you see in the PowerPoint slide. So meters per second becomes meters per second squared. And it's really, really important that you be able to recognize that meters per second squared is the unit of measurement for acceleration. And it doesn't mean this. A lot of students, they say, oh, 0.5 meters per second squared. That must mean that I'm not really done with my question yet. I need to square 0.5, multiply it by itself. No, you don't. Meters per second squared, that's that exponent of 2, that squared unit. It's just that. It belongs to the unit itself. You're just showing that time was used in 2 different ways in this problem to get you to the answer you got. It has nothing to do with furthering your answer along. Again, I'm not going to square 0.5 here into 0.25 or anything like that. So, but you really want to start becoming aware and recognizing that meters per second squared means acceleration. And you could have some variations on that, like kilometers per hour squared or something like that. But whenever you have a distance unit divided by a time unit squared, that's when you know you're dealing with an acceleration problem, or an acceleration unit, excuse me. All right, so we did our practice problems. Now we want to look at the actual assignment. And again, there were 2 links to the assignment in this directions page. I myself, though, I'm just going to go up to course content, go to quizzes, because that's where all of the assignments that are just built into EClass are going to be found. All the multiple choice question type assignments, which this is going to fall into that. And this is the one right here, August 12th, AKS 1A, classwork. Now for you, this looks a little different. Like these 2 right now are hidden from view for you. You should only see this one, but this is my teacher view. And I'm going to go to preview, which again, you won't really need to do. I don't think you even have the option. But one other thing that will change, you'll notice that the attempts allowed are 1. I'm going to change that so that you can have 2 attempts. I'm going to do start quiz. And we're going to work through 2 questions. And question 1 here says, and I think they might be randomized in their order, so number 1 for you might be different. Keep that in mind. But it says a meteoroid changed velocity from 1 kilometer per second to 1.8 kilometers per second in 0.03 seconds. What is the acceleration of the meteoroid? Round to the nearest whole number. Well, it says a meteoroid changed velocity, and it says what is the acceleration. So it tells us to find the acceleration. And on top of that, it says change velocity. Changing velocity means acceleration. So it should be abundantly clear that we want to solve for acceleration. So I'm going to put another little drawing field back up here, or try to. There we go. And I'm going to write our acceleration formula like we did before. A equals VF, again, that means final velocity, minus VI, or initial velocity, the beginning velocity, over time. Or you could say the change in time if you really want, but it's just going to be the total amount of time usually. All right, so the question says it changed velocity from 1 kilometer per second to 1.8 kilometers per second in 0.3 seconds. So which variable is which here? Well, the change in velocity, it goes from 1.0 kilometers per second to 1.8. So the 1.0 comes first, it's earlier, it's initial, and then the 1.8 comes later, it's the final. And don't forget, like the formula says, we want to write our final velocity first in the formula. So it kind of sounds backwards, but that's what we're going to do. So our final velocity is the one that occurs second, and that's our 1.8. So 1.8, and I'm going to leave the units out this time just kind of for time purposes. So it takes a little bit of extra time for me to draw. So 1.8 minus our initial velocity of 1.0 over an amount of time of 0.03 seconds. So I'm going to do a little bit better line than that. That'll work. So do that right here. 0.03, not 0.3, but 0.03 seconds. And so 1.8 minus 1, well, that's just 0.8. Check with a calculator if you want to. And we're dividing that again still by 0.03. You could put a 0 in front of 0.3 if you wanted to. I'm just, again, drawing it to save, or not drawing it to save a little bit of time. And then we actually get to the point where we divide. 0.8 divided by 0.03. And we get 26.66666, blah, 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 blah. So now it did say round up our answer. And the closest answer we have to this is 27. So that is our answer, by the way. And I'll get into why it's not negative 27 in just a second. But let me, 27, bam, right there. And it is kilometers per second squared. So again, the reason why it's not negative 27 kilometers per second squared is because of which velocity was initial and which was final. If we actually reverse the initial and final velocities, like let's say that this car, the meteoroid, excuse me, that's what it was. Let's say the meteoroid was going 1.8 kilometers per second, and then it changed just to 1.0 kilometers per second. Then the 1.0 would be the final, and it would come first in the formula, and the 1.8 would be the initial, and it would go last. And so we would end up doing 1.0 minus 1.8. And that would have given us over here a negative 0.8. And we'd still divide that by 0.03, and then we get negative 27. And notice how I said that. I said that in this scenario, the meteoroid would be going from 1.8 at first to 1.0 later. That's a decrease in velocity. That's slowing down. So if you have a negative acceleration and it's because the final velocity is lower than the initial velocity, that means you're decelerating or you have negative acceleration. So those are complete, the negative 27 and the negative 93 are completely valid answer options, at least in terms of negative being in the realm of possibility. All right, I'm going to go to the next page. We're going to do one more problem together. Now, by the way, do make sure you select your answer before you move on to the next question. I'm not doing that just because I don't actually need to take this right now. But anyhow. Let me draw another little field real quick for this one. This one will be a little bit easier because it's a speed question. All right, so it says, what is the speed of a jet, should say jet plane, not jet place, that travels 550 meters in 5 seconds? So we get out our speed formula, which that looks a lot like a 5. That's a little bit better, maybe. Speed equals distance over time. That kind of looks like an X. Okay, so speed equals distance over time. Our distance is 550 meters. Over our time, which is 5 seconds. And this is going to kind of look like a 55, but it's not. I promise it's just 5 seconds. And so we just divide. Again, speed is a one-step problem. It's usually pretty easy because of that. So we divide 550 by 5. We get 110. Again, double check it on a calculator if you want to. And our unit is meters per second. So that's our correct answer there, 110 meters per second. All right, and that's all we got for now. Just thought this would help you out. Email me if you got further questions, and I will see you later. Make sure you get this done by Friday this week. Thanks.